Now we're going to start Euler-Cauchy equation. Now second order homogeneous linear equations of Euler-Cauchy equation are of the form x square y double dash plus axy dash plus by equals 0, where a and b they are constants. Now this equation per se is not second order homogeneous linear differential equation with constant coefficients, as we have x square and x. And such equations are called Euler-Cauchy equation. Now what we do is, in such equations, we set y as x to the power m. Now y dash will be mx m minus 1, and this y double dash will be m minus 1 x to the power m minus 2. Now we'll substitute these three values in the equation. Now with y square we have x square and then this, so it will be this m minus 1 x to the power m. So here we have x, so it will be again x to the power m. So we can write this as am x to the power m plus b, and y simply x to the power m equals to 0. So from here we'll get this characteristic equation, which is m minus 1 plus am plus b equals to 0, or simply m square plus a minus 1m plus b equals to 0, which is a quadratic equation in M. Now here again we'll have three cases. Case 1, when we have distinct real roots, and suppose the distinct real roots are m1 and m2. So in this case, its solution will be given by y equals c1 x to the power m1 plus c2 x to the power m2. Let us take up an example. Say for example, now here what we'll do is we'll let y as x to the power m. So we can write this as m minus 1 minus 2m plus 2 equals to 0. So it will be this m square minus 3m plus 2 equals to 0. So we'll have two real roots. Either the value of m is 1 or the value of m is 2. Now since we have two distinct roots, we can write its general solution as y equals c1 x plus c2 x square. So that's our first case. Now then we have our second case, when the roots are equal. Now if the roots are equal, in that case m1 will be equal to m2 and will be equal to half of sum of roots, which is minus b upon a. So it will be simply 1 minus a by 2. Now we know one of the solution is y equals x to the power 1 minus a by 2. Now we have to find its second solution, and we have to find its second solution using reduction of order, which we have studied in the previous lecture. So what we'll do is we'll let y2 as some uy1. Now y2 dash will be uy1 dash plus u dash y1, and y2 double dash will be u y1 double dash plus 2 times u dash y1 dash plus y1 u double dash. Now y1 is the solution to this equation, so we can write x square y1 double dash plus ax y1 dash plus b y1 equals to 0, and y2 is also the solution to this equation, so we can write x square y2 double dash plus ax y2 dash plus b y2 equals to 0. Now we'll put the value of y2 dash and y2 double dash. So it will be this x square and this is u y1 double dash plus 2 u dash y1 dash plus y1 u double dash plus ax, and this is u y1 dash plus u dash y1 and plus b y2 is u y1 equals 0. Now what we'll do is we'll take terms of u together. So it'll be this u and then x square y1 double dash plus ax y1 dash plus by1 and then plus terms of u dash together. So we'll have u dash and then it'll be this 2x square y1 dash plus ax y1, and then finally we'll have x square y1 u double dash equals 0. Now we already know this is 0. Now for this second part, what we'll do is we'll take x common, so we can write u dash x and it'll be 2x y1 dash plus a y1. So now we know y1 is x to the power 1 minus a by 2. Now y1 dash will be 1 minus a by 2 x to the power 1 minus a by 2 minus 1. Now if you multiply 2x, then we can write 2x y1 dash will be 1 minus a into x to the power 1 minus a by 2, which is nothing but y1. So we can write this as y1. So it will be 2x y1 dash 1 minus a y1, or simply 2x y1 dash plus a y1 will be nothing but y1. So we can write this as u dash x into y1. So now our differential equation, it reduces to u dash x y1 plus x square y1 u double dash equals to 0. Now we can cancel this x and we can also cancel this y1. We can rewrite this as u double dash upon u dash plus 1 upon x equals 0. Now if we integrate this with respect to x, we can write log u dash plus log x is equal to 0, or we can simply write u dash as 1 by x. Now u dash is du upon dx, so we can write du equals dx upon x, and if we integrate, we can simply write u as log x. We are ignoring the constants of integration. So once we have u as log x, we know that our y2 will be log x into y1, or simply log x into x to the power 1 minus a by 2. So general solution of this equation will be c1 plus log x c2 into x to the power 1 minus a by 2. So that's our second case. Now if we take up an example, suppose we are given a differential equation which is x square y double dash plus 5x y dash plus 4y equals to 0. Now this is Euler-Cauchy form. So simply we let y as x to the power m. So it will be this m minus 1 plus 5m plus 4 equals to 0. So we can write this as m square plus 4m plus 4 equals to 0, or m plus 2 whole square equals to 0. So the two real roots are minus 2 and minus 2. Now we can write its solution as y equals c1 plus c2 log x, x to the power minus 2. Now we'll come to this third case when the roots are imaginary or they are complex. So when we have imaginary roots. Now, if the roots are imaginary, then let us say roots are alpha plus iota beta and alpha minus iota beta. Now we can write x to the power m1 as x to the power alpha plus iota beta, and will be x to the power alpha and x to the power iota beta. Now we can write x to the power iota beta as e to the power log x to the power iota beta, which is x to the power alpha, and this is e to the power iota beta log x. And the same way we can write x to the power n2 as x to the power alpha minus iota beta, and there will be x to the power alpha and will be e to the power minus iota beta log x. Now this case is similar to what we have solved in the first lecture. Now rather than writing them as e to the power iota x and e to the power minus iota x, we'll take their linear combinations. So if we add them, we'll get cos, and if we subtract them, we'll get sine. So we want to write its general solution as y equals x to the power alpha c1 cos beta log x plus c2 sine beta log x. So if the roots are imaginary, then we'll have this solution as y equals x to the power alpha c1 cos beta log x plus c2 sine beta log x. Now we'll consider an example. Say for example, suppose we have to solve this differential equation, which is x square y double dash plus 7x y dash plus 13 y equals 0. Now again we let y as x to the power m, so it will be this m minus 1 plus 7m plus 13, it is equal to 0. So we can write this as m square plus 6m plus 13 equals to 0. Now this is m plus 3 whole square plus 4 equals to 0. So value of m is minus 3 plus minus 2 iota. Now this is your alpha and 2 is your beta. So we can directly write the solution as y equals So this is how we solve Euler-Cauchy equation.